How are you all doing this morning?
Doing great.
Cool deal. Well, hopefully you guys had a chance to watch the review of Sinusoid's lecture. Today for our in-class assignment, it's going to be dealing with a lot of trig identities. So, excuse me, let's jump right in here. So this first problem, the first two parts are fairly straightforward, and then the third one can be rather difficult, and so we'll work it in different ways. So part A here, different color. We are asked to express each of the following sinusoidal functions as a single cosine function. So that means our expectation will be, let's see, that x of t will be of the form x naught, which is our magnitude of our cosine function, cosine omega t, whatever our angular frequency is, plus some angle theta x, which is the phase angle. So our goal is to convert all three of these into that form that I've just written. So for part A, we are given a sinusoidal function, a sine function specifically. So if we apply the trig identity sine of theta is equal to cosine theta minus 90 degrees, we find that f of t is going to simply be 300 cosine 628t minus 90 degrees. Nothing particularly wild about that one. It's just a simple application of one of that list of trig identities that's there on the right-hand side of my video. For part B, we have g of t is equal to -4 sine 3 pi of t plus 30 degrees. So we're going to have to apply two trig identities. So we can apply negative sine of theta is equal to sine of theta plus or minus 180 degrees to get rid of the negative sign first, which gives us g of t is equal to 4 sine 3 pi t plus 210 degrees. And then we can apply that same trig identity from our first problem. Sine theta is equal to cosine theta minus 90 degrees, which gives us g of t is equal to, let's see, 4 cosine 3 pi of t, 210 minus 90 is 120. And I think that's it, yeah. Part C is going to be significantly more difficult depending on the approach we take. So there's a trig identity. It says that sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. Okay. If we apply this trig identity, we find that h of t, which was originally, let's see, 14 sine 50t minus 5 degrees minus 10 cosine of 50t. So if we apply that trig identity, we can get 14 times sine 50t cosine 5 degrees, where all I've done is I've set alpha equal to 50t and beta equal to 5 degrees. And then we'll have cosine 50t sine 5 degrees minus 10 cosine 50t. Keep on with this math. That gives me 14 cosine 5 degrees times sine 50t minus 14 sine 5 degrees cosine 50t minus 10 times cosine 50t. And I can group like terms. Well, actually, I don't need, let's do one more step. So notice here that 14 cosine 5 degrees. Cosine is just a ratio. It's a number that's going to be between -1 and +1, right? So 14 cosine 5 degrees is just a number. Same with 14 sine 5 degrees. So if we evaluate that, we get 13.947 sine 50t minus 1.220 cosine 50t minus 10 cosine 50t is equal to negative 11.220 cosine 50t plus 13.947 sine 50t. So we've applied a trig identity and done a considerable amount of math here to get roughly halfway through our problem. And let me explain what I mean by that. We can use another trig identity that says that cosine of alpha plus beta is equal to cosine alpha, I need to use the parentheses there, cosine beta minus sine alpha sine beta. And why we're going to be using this, what I'm going to do here, actually, I'm going to multiply through by a factor of a, where a is just an amplitude function. And so we can actually see, if we equate these two, this is the form of our final answer that we're looking for. We want a magnitude cosine alpha, which in this case would be 50t, plus beta, which is just going to be some phase angle. And right now, we have it in the form to where we have some number, which is going to be minus sine alpha, right? So we have a cosine term and we have a sine term. So we can say that a cosine beta is equal to negative 11.220. And similarly, we can say that a sine beta is equal to negative 13.947, where that negative sign on the a sine beta comes from the part here where we are expecting a sine beta to be negative, but up here we have a positive sign. So we have to flip the sign there. So now we can use a few more trig identities. For instance, since cosine squared theta plus sine squared theta is equal to 1, well, that means a cosine theta squared plus a sine theta squared, let's see, is equal to a squared times cosine squared theta plus sine squared theta is equal to a squared, we can say, I'm running out of room here. Let me edit document. Yeah, I'll sneak it in there. I can say that the square root, or a, is going to be equal to the square root of a cosine beta squared plus a sine beta squared, which gives me 17.900. And I know that tangent theta is equal to sine over cosine, which implies that theta is equal to the inverse tangent of a sine beta over a cosine beta, and I'll get negative 128.817 degrees. If I put those results together, I get h of t is equal to 17.900 cosine 50t minus 128.817 degrees. So that is a whole lot of horrifying math. I've applied the trig identities and all that kind of stuff, but I would not be surprised if at least some of you guys had difficulty following through with all the math that I just did. So what I'd like to do real quick is take a quick aside here, okay? So one of the last trig identities on my list was Euler's identity, which said that e to the j theta was equal to cosine theta plus j sine theta. So my original complex number, h of t, was 14 sine 50t minus 5 degrees minus 10 cosine 50t. What I'm going to do is I'm going to convert that sine to a cosine function. So that would give me 14 cosine 50t minus 95 degrees, because to convert from sine to cosine, I subtract 90 degrees, minus 10 cosine 50t. And this is where things are going to maybe get a little bit weird. I can say that 14 cosine of 50t is the real part of the complex number 14e to the j 50t minus 95 degrees. And let's see, so I should have a minus sign. The real part of 10 e to the j 50t, and let's call it plus 0 degrees to be clear here. Or in polar form, this looks like real 14 angle negative 95 degrees minus the real 10 angle 0 degrees. So one of you guys that understands how to use the complex numbers on your calculator, don't do real 14 angle 95 minus real 10 angle 0. Just do this complex number minus this complex number, please. Actually, I think that the issue is my notation here. Anybody get an answer for me yet?
I think I did. I'm not completely sure. I think this would be in polar form or the regular form, or it's like the, so it's negative 11.22 minus 13.946 I.
All right, I'll negative 11.22 plus J 13.946
minus 13.
minus 13. All right. So those numbers should hopefully look fairly familiar because that this negative 11.220 we found to be a cosine beta, and this negative 13.946 we found to be a sine beta. If you could, though, to make things a little bit easier on us, could you convert that rectangular form complex number into a polar form complex number? So what kind of calculator do you have?
I have the TI 36.
All right, so just take your answer, hit second pi, and then 4.
Well, I think I might have did something right before that to.
Okay. We'll just type in negative 11.220 minus 13.946J, and then second pi 4.
Okay, hold on.
Get a little bit of rounding error, but it'll be okay.
Okay, 17.899.
So on my calculator, I'm getting 17.8998, which I'd call 17.9.
Okay, yeah. And then the angle of minus 128.81.
All right. And so the real part of that is going to be 17.900 cosine 50t minus 128.81 degrees, which is the exact answer that we are looking for. So we can actually use complex numbers to do the addition and subtraction and all that kind of stuff of sinusoids that our calculators can't do, and get the exact same result in a much more straightforward fashion. So I went through this process applying Euler's identity and all that kind of good stuff just to, sorry, this shouldn't be there, just to show you how it's done. But in the future, you really only need to convert both things to cosine functions, and then magnitude phase angle of the first one plus or minus magnitude phase angle of the second one, just depending on what it is. So for example, this is not in the in-class assignment or anything, but if we had, let's see, K of t was equal to 13 cosine 20t plus 35 degrees minus 8 sine 20t plus 10 degrees, we could get the exact correct result by simply saying this is 13 angle 35 minus 8 angle negative 80 degrees. We would not need to go through all those terrible trig identities or anything else. The complex numbers take care of that all for us. So this is the, I guess, the first introduction as to why the heck we're going to be using complex numbers when we're analyzing these circuits. We have these, we're going to have time domain voltages and currents that we're going to need to add together to do KCL and KVL. And if we do it in the time domain, it's going to take us forever to apply 40 trig identities. Whereas if we do it using complex numbers, which is more commonly referred to as the frequency domain, we can do all of that math very, very trivially with just a basic calculator. So on your homeworks and all that kind of good stuff, you're going to be asked a lot of problems similar to these in-class assignments. If you want to brute force your way through using trig identities, you know, more power to you. But the expectation here is that you should be applying your complex number relationships to do the math to make your life so much more simple. All right. Problem 2. We're asked to determine the angle by which I of t leads V of t if V of t has some specific value, and then we're given, I think, for the current. And so I'm going to answer this question using the concept of a phase diagram. Did I go over phase diagrams in my video lecture at all?
Yes, it's the diagram where you're putting the angles and then you just basically go counterclockwise or clockwise, right?
Exactly right, yeah. So all that really is just taking a snapshot of the sinusoidal functions at a specific instant in time, particularly t is equal to 0. So let's make our voltage waveform in red, so 10 angle negative 45 degrees. And here the magnitude doesn't particularly matter. So this is V of t. So we have an angle of negative 45 degrees like so. And then IA of t, I'll do it in blue, we have 5 cosine 10 degrees. So that's going to be here on this axis with an angle of 0, where this is 0 degrees. Just to be clear, 0 degrees, 90 degrees, plus or minus 180 degrees, and negative 90 degrees. So we want to determine the angle by which I1 leads V of t, where IA is our curve in blue. Since we want to know the angle by which I1 leads V of t, we start measuring from V of t, and because we want leading, we're going to measure counterclockwise. I believe. And so we can see that IA of t leads V of t by that angle. So we start measuring from V of t, and 45 degrees later we hit IA of t. So IA leads V of t by 45 degrees. It's that simple. So I'm going to erase this. And now let's look at IB of t. I'm going to ask you guys some questions. So let's see. IB of t is with an angle of negative 80 degrees. So it's going to be over here. So since I still want to know by how much I leads V, I'm going to start measuring from V and go all the way around like this to I. So from this, I B of t leads V of t by how much? Anybody got any ideas? So we know from here, oh, sorry, go ahead.
I was going to say positive 325 degrees.
Right, we know from here to here is 45 degrees. From here to here is another 90. From here to here is 90. From here to here is 90. And from here to here is 10. So 45 plus 270 plus 10 is 325 degrees. Now, before we go on and do the third part here, you're going to be asked questions like this on your homework as well. And there is a slight issue with web work. And that is that the way that the problem is currently configured, and I just learned about this the other day while I'm teaching myself how to program new problems in web work. But the problem is that web work, as it's set up right now, does not understand that, say, negative 360 degrees, 0, positive 360 degrees, 720 degrees, etc. All of those things separated by exactly 360 degrees. Web work does not understand that those are all equivalent angles. So you might do this exact process, which is perfectly correct, put in the answer in web work, and it tells you that you did the problem wrong. All you need to do is add 360 degrees to your original answer, and if that isn't correct, subtract 360 degrees from your original answer. One of those is set to be correct just based on how the person who originally set up these assignments wrote the problems. So you're doing it correctly. It's a limitation of web work not interpreting the fact that angles that are 360 degrees separated are identical. Does that make sense?
Yes, sir.
Okay. So I C of t then should be fairly straightforward. I feel like maybe not beaten to death, but I feel like we have a pretty good grasp of what's going on here. So I C of t, what are we going to need to do to it? Excuse me.
We have to convert it to the cosine.
Absolutely right. Yeah. So if you have a sinusoidal function, you need to convert it to a cosine so that everything is on the same scale effectively. So 5 sine 10t plus 149 degrees is going to be 5 cosine 10t plus what?
59 degrees.
59 degrees. Absolutely right. And so 59 degrees will be aligned somewhere in our first quadrant. So I'm not going to do anything else. You guys should be able to tell me what the angle by which I C of t leads V of t just based on this. So how would I go about figuring that out?
45 plus 59.
It is literally that simple. That's correct. So I start measuring from V of t. I go up 45 degrees to hit 0. I go 59 more degrees. 59 and 45 is 104 degrees. So leading and lagging, students have an awful lot of trouble, typically speaking, understanding it. And I'm not entirely sure why, because if you just use a phase diagram like this, it seems rather trivial to me. Maybe I'm just a jerk, but I don't know. It seems pretty straightforward. So any questions there on problem 2? Just to be clear here, we wanted the angle by which I leads V, so we always start at V, and because we want leading, we go counterclockwise. If we wanted lagging, we would go clockwise. All right. Express the following time domain signals as phasors in the frequency domain. So I'm not. I told you guys specifically to just make sure that you watch the video on the sinusoidal review. So some of you may not have watched the introduction to phasors and all that kind of stuff. Or I think I titled it "Steady Force Response Due to Sinusoidal Excitation" or some stuff like that. But all that, the gist of that whole big ugly thing really was that instead of working in the time domain like we have here, we could work in the frequency domain. So I'm gonna write a little table for this. So we're gonna have a time domain representation. And time domain means that we're going to be having signals. Let's just arbitrarily say it's a voltage signal. V of t is equal to Vm, which stands for the magnitude of the voltage waveform, cosine omega t plus some phase angle theta v. We could work in what I call the mixed domain, where we recognize that V of t is simply the real part of the complex number Vm e to the j omega t plus theta v. And working with complex numbers in this form does make things a little bit easier. Or we can work fully in the frequency domain with phasors. And a phasor is just a shorthand notation for the mixed domain, where we've suppressed our frequency component. So in the frequency domain, we will have a phasor voltage V that is simply the magnitude, angle, the phase angle. That's it. But they're all based on the cosine. And another constraint is that Vm must be positive. That's it. So the conversion from the time domain and to the frequency domain and vice versa should be fairly straightforward. So if we look at part A here, we can notice that it has a negative magnitude. So we're going to have to correct that to be a positive magnitude. How would we do that?
You would change the angle to the opposite, so like 180 minus 75.
Okay. So not 180 minus 75, it'd be 75 minus 180.
Yeah.
Okay. So this would be 10 cosine 4t. 75 minus 180 degrees is negative 105 degrees. So that means that VA, our phasor, what's the magnitude of our time domain VA? That's the magnitude. What's that number?
10.
10. What's the phase angle?
Negative 105.
Congratulations, we have just converted the signal into the frequency domain. It is literally that easy. You take the angle, so you convert it to a cosine function with a positive magnitude, then you take the magnitude and the phase angle, and that's the only pieces of information you keep to make it a phasor. It's pretty straightforward. All right, so let's look at VB here. How are we going to convert that to a cosine function with a positive magnitude?
You take the angle and subtract 90 degrees.
Yep, so 5 cosine 20t minus 100 degrees volts. So what is my phasor voltage VB going to be?
Five angle negative 100 degrees.
That's absolutely correct. All right, so here we're running into something a little weird. Our VC of t is the sum of two sinusoids. So let's not go through the headache of converting this guy using trig identities. We could say that this is going to be 4 cosine 2t plus 25 degrees plus, using what we did just in the last problem, we're going to convert that sine to a cosine by subtracting 90 degrees from the phase angle. So that's plus 3 sine 2t minus 90 degrees. So our phasor representation VC is going to be 4 angle 25 degrees plus 3 angle minus 90 degrees. And we can do this complex math and figure out what that is expressed as a single complex number. So what's that going to be in polar form, please?
I got 3.625 minus J 1.309.
So 3.625 minus J, what was that?
1.309.
All right, and could you convert that from rectangular to polar for me, please, sir?
I got 3.85 angle negative 19.86.
Alrighty, and that appears to agree. So I don't particularly care whether you work in rectangular or polar. I prefer polar roughly 90% of the time, but there are times when I'll work in rectangular. And I couldn't really even begin to explain why I work some things in polar and some in rectangular. So whichever one you're more comfortable with is perfectly fine by me. I just wanted everybody to see that this number is absolutely correct, even though it's not explicitly that answer. So converting from the time domain to the frequency domain, hopefully pretty dang straightforward, nothing wild or crazy there. Convert it to a cosine function with a positive magnitude, and then erase everything but the magnitude and the angle, and you've got it. All right, impedances. I don't know. Let's save this guy for Thursday, because I think I may be overwhelming you guys with too much stuff in one lecture. So we'll save this guy for Thursday after you have a chance to review some material that I've posted regarding phasor domain relationships for voltage and current in all of the components that we regularly talk about. So yeah, typically speaking, in a live lecture session, I spend pretty much the full 1 hour and 50 minutes talking about all this stuff, and we don't ever get a chance to actually do the in-class assignment. So I think splitting this up will be more beneficial to you guys to be able to actually have time to process the information. So for Thursday, then there's going to be a brief video on phasor relationships for voltage and current. Then we're going to talk about the concept of impedance, which is just the steady state sinusoidal version of resistance. And I want to say I also have some stuff there about admittance. And we're not really going to talk about admittance in this class. I recycle that lecture for my Circuits 2 class, which is why it's there. It's not going to hurt you guys to learn about admittance in any way, shape, or form, but we are not going to be dealing with it in this class. In addition to that lecture on phasor relationships, impedance, and admittance, I will post a video about like an introduction to steady state sinusoidal circuit analysis. And what that's really going to be is just using the phasors that we've talked about in this problem and the concept of impedance that we'll talk about for Thursday, using those concepts together and applying DC circuit analysis techniques to solve problems. So I'm going to post those 2 videos, and then we might spend maybe 10 to 15 minutes talking about things before we jump into the in-class assignment, if that sounds okay to you guys. Because I strongly feel that at least some of you should have some questions about what the heck we're doing, because it's not really an intuitive leap. Okay, so unless anybody has any questions about what we've covered today, I think we can get out of here and reconvene on Thursday.
All right, see ya.
Thank you.
No problem. You guys have a good day, and yeah, I'll catch you guys on Thursday.